Have you ever wondered why the medicine you take works so well? It's not just about the chemicals inside, it's also about how big, or rather how small those chemical particles are. In the world of pharmacy, size is a very big deal. For a drug to work, your body has to absorb it. Smaller particles have a much larger surface area compared to their volume. This means more of the drug is exposed and ready to dissolve quickly into your bloodstream. It's like trying to dissolve a giant sugar cube in your tea, versus a spoonful of fine sugar. The fine sugar disappears almost instantly, right? That's exactly what we want our medicines to do. This process of making big particles into tiny ones is called size reduction, or comminution. It's one of the most fundamental steps in making effective medicines. When drug particles are too large, they might not dissolve properly in your stomach or intestines. This could mean you don't get the full dose you need, making the treatment less effective. In some cases, like with asthma inhalers, the particles must be microscopic to travel deep into your lungs, so making things smaller isn't just for convenience, it's a critical part of designing a drug that truly helps people. Now, how do we get these particles so incredibly small? So, what exactly is a fluid energy mill? Let's break it down. The name gives you a big clue. It's a mill, a machine for grinding, that uses the energy of a fluid. This fluid is typically a gas, compressed air, steam, an inert gas like nitrogen. The mill creates a super-fast, turbulent stream of this gas inside a chamber. We introduce the drug material into this chaotic whirlwind. The particles get caught up in the high-velocity stream. They are accelerated to incredible speeds. The magic isn't from particles hitting the walls, it's from particles crashing into each other. Core principle, impact. Core principle, attrition. Imagine two tiny cars speeding toward each other in a wind tunnel and colliding. They'd shatter into smaller pieces. That's impact. Now imagine particles scraping and rubbing as they fly. That's attrition. Millions of these collisions and abrasions happen every second. That constant smashing and scraping breaks particles into superfine powder. The grinding medium is the material itself. This is called micronization. We're making micro-sized particles. At first glance, a fluid energy mill might look like a complex maze of pipes and chambers, but its design is actually quite clever. Think of it like a team where each player has a specific role. The main body of the mill is the grinding chamber. This is where all the action happens. These chambers come in different shapes. A common design is a circular loop, an oval-shaped loop called a pancake mill or loop mill. This shape creates a vortex, a swirling tornado of gas that keeps particles moving and colliding. The next crucial part is the set of high-pressure nozzles. They act like tiny jet engines pointed into the grinding chamber. A powerful compressor feeds filtered, dry air to these nozzles at very high pressure. The nozzles are precisely angled to inject gas to create a strong, turbulent, rotating flow inside the chamber. To feed material into the mill, we use a feed inlet equipped with a Venturi feeder. The Venturi uses suction from high-speed gas to pull coarse powder from a hopper and introduce it into the grinding chamber. Finally, how do we get superfine particles out while keeping big ones in? The classifier does that job. Smaller, lighter particles are drawn inward to a central outlet port and exit the mill with the gas stream to be collected. Let's walk a particle through its journey in a fluid energy mill. Imagine our particle is a tiny grain of a drug substance, maybe about 100 microns in size, still pretty small, but honestly, too big for our needs. First, this grain is loaded into a hopper. Venturi feeder whoosh, injected into the grinding chamber. The moment it enters, it's hit by an incredibly fast jet of air moving at hundreds of meters per second, sometimes even approaching the speed of sound. This is sort of like stepping into a hurricane that's happening inside a metal donut. The particle is immediately accelerated. Once inside the turbulent vortex, our particle is no longer in control. It's sent spiraling around the chamber at extreme speeds. It's in a chaotic dance with millions of other particles. Suddenly, bam! It collides head-on with another particle that was going just as fast in a slightly different direction. The impact is so violent that both particles shatter, breaking into several smaller fragments. But the journey isn't over. These new, smaller fragments are instantly swept back up into the swirling gas stream, continuing their high-speed race around the chamber. Acceleration-collision fracture happens over and over again, thousands of times a second. It's kind of like a pinball machine for particles, but instead of bouncing off bumpers, they are smashing into each other. With each collision, the particles get smaller and smaller. Now, our particle has been broken down into a tiny fragment, perhaps only 5 microns in size. It passes through the classifier outlet and exits the mill, its wild ride complete. So this technology is cool, but where do we actually use it? The applications in pharmacy are vast and incredibly important. One of the biggest areas is in creating medicines for inhalation. Think about an asthma inhaler. For the medicine to work, the drug particles must be small enough, typically under 5 microns, to travel past the throat and deep into the tiny airways of the lungs, the bronchioles. A fluid energy mill is the perfect tool for this job. It can micronize drugs like salbutamol or budesonide into an extremely fine powder that can be carried by the propellant and delivered exactly where it's needed to open up the airways. Another major application is improving the bioavailability of poorly soluble drugs. Many new drug molecules are like oil and water, they just don't dissolve well. If a drug doesn't dissolve in the GI tract, it can't be absorbed into the bloodstream. By reducing particle size with a fluid energy mill, we dramatically increase surface area, so the drug dissolves faster and more is absorbed, giving a more effective and reliable therapeutic effect. Fluid energy mills are also essential in the production of sterile products, especially injectable suspensions and ophthalmic ointments. Particle size must be small and uniform to prevent irritation and ensure smooth delivery through a needle or onto the eye. A fluid energy mill can be operated using sterilized air or nitrogen, and because it's a closed system, it's possible to micronize under aseptic conditions. This prevents contamination and keeps sensitive products like steroid eye ointments safe and effective. It's a versatile tool that touches almost every form of medicine we make. Like any piece of technology, the fluid energy mill has a fantastic set of advantages, but also a few limitations to consider. Let's start with the good stuff. The number one advantage is the incredibly fine powder it can produce. It's one of the best methods out there for achieving particle sizes in the low single-digit micron range. Many mechanical mills struggle to reach those sizes. This ultra-fine powder is often more uniform in size. Consistency is golden in pharmacy. It leads to more predictable dissolution rates. Another huge plus is the lack of heat generation. Traditional grinding creates friction and heat. Heat is a disaster for thermolabile drugs. The fluid energy mill uses cool, compressed gas. Since there are no moving grinding parts, there is virtually no contamination from the mill itself. Now for the flip side. A major disadvantage is high energy consumption. Compressing huge volumes of gas to high pressures requires a lot of power. That makes these mills expensive to operate versus some mechanical alternatives. Another challenge, high-velocity particles can be abrasive. The particles can wear away internal surfaces, especially at bends and nozzles. Finally, fluid energy mills aren't suitable for all materials. Soft materials can agglomerate. Waxy substances can coat surfaces. Sticky materials clump and foul the chamber.